rational functions. A rational function is a function consisting of a rational expression numerator and denominator, is called a rational function. There are basically three ways to break a rational function. The first of them is a horizontal asymptote. Essentially what this is, it's a break in your graph, your rational function. This is your y, this is your x-axis, and it's horizontal. And when it faces a function, the function will hug it. It will never reach where the horizontal asymptote ends, but it will come as close to as possible. And then another way for it to break would be your vertical asymptote. Similarly, on your graph, to your horizontal, but instead of being horizontal, it's going to be vertical. And when faced with a function, it will hug it until infinity. The third way is they're holes. And that will essentially be if you have y and x. If you have a function of some sort, it will be a point where it does not exist, as you can see right there. So, the first example we're going to do, as soon as I erase this board, of a rational function. Okay, first we're going to learn about vertical and horizontal asymptotes. So, example 1 is going to be f of x equals x over x minus 3. So, vertical asymptotes, what you would do is you'd set this denominator equal to 0. So when x minus 3 equals, I'll label it for you guys. This is for our vertical asymptote, our VA. So setting the denominator equal to 0, x minus 3 equals 0, x will be equal to 3. That's where our vertical asymptote is. So when we make our graph, y, x, the marker's dying out a little bit on me, so I'm going to switch it up. Okay, x equals 3, 1, 2, 3. Our vertical asymptote will run right through 3 just like that. Next thing we're going to search for is if it has a horizontal asymptote. Now, if the increment of your highest value, a value of x, is equal, such as this one, the exponent is 1, x of 1, x of 1, that means there will be a horizontal asymptote, x over x, just like this. See how they're equal? So our horizontal asymptote will be x, which equals 1. Because it should always cancel out, but in this case there's just a 1 before it, just like that. And there's no holes in this graph because we didn't cross anything out, but I'll show you an example of that in a second. So the horizontal is at y equals 1. So at 1, there is a horizontal asymptote. Now we just got to plot where our functions lie within this graph. We're going to go on the negative x direction and the negative a positive x direction of this graph to see where it is. So when f of x is equal to 0, because that's an easy point to plot on the negative x direction, you have 0 over 0 minus 3. So it would be equal to 0 over 0. This is going to be our x-intercept. So when x equals 0, because that's equal to 0, obviously. X equals 0, our y is equal to 0, making our x-intercept 0, 0. And to find the y-intercept, we're going to set our equation x over x minus 3 equal to 0. But since this is 0 multiplying it by something, you're only really going to compute when what the numerator is equal to 0, because no matter what, when you multiply by 0, it's always going to cancel out. So you're always just going to set the numerator equal to 0 to find the y-intercept. So this is the x-intercept, and so this is the y-intercept. So when y equals 0, x equals 0. So 0, 0, as you can see, is obviously the same because it's 0, 0. And now we're just going to find a few more points, such as, let's try x equals 1. F of 1 equals 1 over 1 minus 3, and that equals 1 over negative 1/2. So another point we're going to do is x equals 1, y equals negative 1/2. So at x equals 1, negative 1/2, because this is about where negative 1 is, so 1/2 right here. And when knowing what an asymptote does, you know it's going to hug the lines. So our curve is going to look just like this, and it's going to go into infinity. Now, what we're going to do is we're going to find the other side of our graph, because there's not going to be multiple, obviously, on this points, but there will be something on those two quadrants. So another point we're going to find is after 3, so I'm just going to choose x equals 4. So f of x equals 4 equals 4 divided by 4 minus 3, that equals 1. So when x equals 4, y equals 4. So 1, 2, 3, 4, 4, 4, 4, 4. And then we can just assume from this graph, just like the rest, the curve is going to go this way, because it's always going to hug those asymptotes. Now we're going to try another example to find a hole in our rational function.
I don't think I'm paying you enough.
So for this next one, we have an equation f of x equals x plus 2 x minus 1 over x plus 2. And in this example they've given us, you can see it's already factored, but most of the time you will have to factor it yourself to find out the canceling elements. In this example, x plus 2 is obviously going to cancel. And when they cancel, that means there's a hole in the graph. So, x plus 2 equals, x equals negative 2. So we're going to plug that into our initial equation to find where that hole is, because this is our x component when it cancels. But our y component is, x is negative 2 minus 1, because we're plugging it back in because that cancels. Our y will be negative 3. So the hole is at negative 2, negative 3. With this graph, it's just going to be a simple line. Y, x equals negative 1, that's our intercept. And then it's just increasing by 1s. So, and then our hole is at negative 2, negative 3. So 1, 2, negative 2, 1, 2, 3, negative 3. But since it's our hole, this is where it is. You're gonna erase that and make it a hole, because that's where it does not exist. And now we're gonna try one more example to put all of this that you've just learned together. So we got 3 types of breaks: horizontal, vertical, and holes. Okay, so now we're going to do an example of this, putting all we've learned together. So the example is f of x equals 4x squared plus x minus 3 all over x squared minus 1. And as you can see, this is not factored, so we don't know what to cancel out yet. So when we factor the bottom, x squared minus 1 is of course x plus 1, x minus 1, and when factoring the top, I like to use the Australian method. So it's our a is 4, our b is 1, and our c is negative 3, but to get this side, we're going to multiply a times c, which equals a negative 12. And what you add to get 1, and you multiply to get negative 12, is positive 4 minus 3. This cancels out, so it's 1 over 1. Sorry for the phone call. So what we get in factored form is x plus 1 and x plus 1 and 4x minus 3, because the bottom half is the x component, top is the number component. So when we simplify this, our new equation should be f of x equals x plus 1, 4x minus 3, all over x plus 1, x minus 1. I'm just going to erase this so we have some more room, because this is a graphic equation, and you've already seen how I got that. Alright, so looking at this, right automatically you can see that there is a hole in this equation because the x plus 1 cancels out. To find that hole, what we're going to do is set x equal to negative 1, because that's where the hole is, x equals negative 1. And we need to find the y component of that hole. So we put it into the equation, and we're going to use our factored form because it's going to be easier, and obviously this cancels out to 1. So it's going to be 4 times negative 1 minus 3 over negative 1 minus 1. Negative 1 minus 1 is negative 2. That's negative 4. Negative 4 minus 3 equals negative 7 over negative 2. The negatives cancel out. So our hole is going to be negative 1, 7 over 2. The next thing we have to find is our horizontal and vertical asymptotes. Now right away, when we're looking at this equation, we can see that there is going to be a horizontal asymptote. And that's because the degree of the x component is equal in the numerator and the denominator. So for a horizontal asymptote, y equals 4x squared over 1x squared. Obviously the 4x squareds cancel out because they are the same value. And so y equals to 4 for a horizontal asymptote. As for our vertical asymptote, it's when we make the denominator equal to 0. And when x minus 1 is equal to 0, the vertical asymptote will be x equals 1. Now we're going to make out a graph to show this. Y, x, vertical asymptote, x equals 1. That's 1. And then our horizontal asymptote is y equals 4. 1, 2, 3, 4. And then you're making your asymptote. Now we have a hole at negative 1, 7 over 2. So negative 1, and then 7 over 2 is about 3.5. So it's going to be somewhere around here. So that's where our hole is, and to make it a hole, make it a little hole. And now we're just going to plot some other points. So I'm going to erase this. I hope you already have it down in your notes or understand it, so that we can compute out some points to graph. Now, let's just just find x equals -2. So f of -2, and you can put it back in this equation because once again the x plus 1's cancel out to 1. So 4 times -2 minus 3, that's -8 minus 3 equals -11 over -2 minus 1 equals -3. So this is going to be positive on account of negative over negative. So 1 point is going to be -2 over 11 over 3. 3 divided by 11 is about, because 3 times 3 is 9, and it's going to be 3 2/3. So -2 right here, and then 3 2/3 is a little bit closer to your asymptote, and so you know that your function is going to look somewhat like this because it's always going to hug it. Of course, you should always find your x and y intercepts, which is when they're equal to 0. I should have done that first, forgive me. So when your x is equal to 0, that's going to be your y-intercept, which really, once again, you're only setting your numerator equal to 0 because the denominator will always cancel out. So it should be 4x equals 3, x equals 3/4 when y equals 0. So it's going to intercept the y-axis on 3/4, which is about right here. So once again, you can see that my line was essentially. So I made a small mistake just with my words. So when we're finding our x-intercept, it's when you're making y equal to 0. So when y equals 0, x equals 3/4. And then our y-intercept is when x is equal to 0. And that is when we make this whole equation equal to 0. The x component is equal to 0, which is 4 times 0 minus 3 over 0 minus 1. Those are zeros, so it should be 3 is when y equals 3 when it's hitting the y-axis because it's intercepting. So y-intercept is going to be 0x, positive 3. X-intercept is 3/4 x, 0y. So that means that it's going to be hitting our y-axis at 3, which is right here, which is still going to make this curvy little graph. And then our x-intercept is 3/4. So once again, it's about right here, because let's say that this is 1, and so this right here is going to be 3/4, making that our intercept. Now we want to find something on the other side of the asymptote, which is 1, so we're going to set x equal to 2 as opposed to -2. I'm going to do it up here so you can keep seeing the intercepts and how I found them. So f of 2, because it's on the other side of this asymptote we can't reach, we're going to use this simplified equation. So 4 times 2 minus 3, that's 8. 2 minus 1, that's 1. So 8 minus 3 is 5 over 1. So our next point is 2.
Somebody gave you a great job.
It's fine. Thanks, Mom.
And no, I'm just telling you.
Mom, I'm kind of in the middle of filming. They can hear you. Thank you. Coming back. So our next point on the other side of the asymptote is 2, 5. So x will be 2, like I said, and our y will be 5. 1, 2, 4, and then this should be 5. And then it's always going to hug the asymptote like that. So our graph should like that, and you have a hole right there.